Okay, Assalamualaikum warahmatullahi wabarakatuh. So we continue with the second lecture for week number 1. So we want to describe the radiation field. Okay, radiation field. So when the radiation passing through the point of the molecule, how it affect the molecule. Okay, so we want to see that. Okay, so these are the examples. So if we see that we shoot an arrow to a point, target located 1 kilometer away. So how many arrow will hit the target, or how many arrow will miss the target? Okay, so if we consider a point, so this is a point target in the field of ionizing radiation. So how many ray will strike P per unit time, or if we're not striking the P, it can also affect uh, the P, okay, the energy of this molecule P. Okay, so these are just like in our radiation, the counting statistic. Okay, so how many radiation or how many particle passing through the point. Okay, so here we want to describe this radiation field. So how many radiation passing or hitting the target. Okay, so to describe the radiation field at the point P, need to define, so we need to define the non-zero volume around it. Okay, so because as we say here, how many arrow will hit the target if the point is located 1 kilometer away. Okay, so we need to define the non-zero volume around the point. Okay, so here we can use the stochastic counting or non-stochastic counting. Okay, non-stochastic physical sphere quantities. Okay, so here we can see that these are the point P and these are the passing ray. Okay, so here we can change the volume, or the volume depend on the time, or the mass depend on the time. So the the width or the rank, the spare, the point or the area of the point. Okay, so we can use this graph as our starting point. Okay, so first we see the stochastic quantities. Okay, so stochastic quantities, it value occur randomly and hence cannot be predicted. Okay, contohnya macam spontaneous emission. Okay, spontaneous emission. So if we wait for let's say 1 hour, nothing happen. But when we wait for another 1 hour, maybe 2 or 3 radiation passing through the point. Okay, so that is randomly happening. Okay, so the probability of any particular value is determined by the probability distribution. So we use this probability distribution like our PDA. It is defined for finite domain only. Okay, so we have non-zero volume. So the expectation value, okay, of counting the occurrence of the radiation. Okay, so this is the NE, expectation value. NE is the mean of its measured value for infinite number of measurement. Okay, so here you can see that we like I said, we wait for 1 hour, nothing happen. We wait another 1 hour, 2 or 3 radiation coming, and we wait for another 1 hour. So we do the summation and taking the mean or the average of the radiation for that hour. Okay, so this n bar is the measured value n of n as number of n observation approach infinity. Okay, so we measure it again and again and again and again, and we do count the number of radiation coming. Okay, so for a constant radiation, Okay, so this one constant radiation. So if we have, we can control the radiation. Okay, so radiation with respect to how many rays arrive at a given point per unit area at a time interval. So let's say 1 hour, 3 radiation or 3 particle coming. So next hour, 3 particle coming. So we can use the Poisson distribution. Okay, so here we need to take note that, so this one we assume that our detector is very efficient and time interval also fixed and no systemic change of the field versus time. Okay, so this field. Okay, so we don't move, for example, we do not move the detector. Okay, so the probability of X occurrence in an interval is given by this Poisson distribution. So we know from our PDA, X bar X exponential minus X bar over X factorial. Okay, so these are the example. Okay, so you see that we have 100 people. So how many person has their birthday today? Okay, so the probability density is 1 over 365, 0.024. The number of person 1000, or the number of counting and experiment is 1000, so n,000. So the mean is equal to n times p, so 2.75, and the standard deviation is 1.66. Okay, so here we can choose. Here we can choose any day, 365 or 364, 264. So we can get this Poisson distribution like this Px. Okay. So next, if the Gaussian distribution. So for a large number of event, so many radiation coming. Okay, so for radiation, so the counting can be approximated by this Gaussian distribution. Okay, so these are just repetition from our PDAs. The standard deviation of a single random measurement and the number of particle. Okay, related to NE is equal to sigma square root of NE equal to n bar, and the corresponding percentage standard deviation is 100 over square root of n bar. Okay, so we can get this value. So the number Gaussian distribution. Okay, so we have this Fn equal to 1 over sigma square root of 2 pi exponential minus n minus n bar squared over 2 sigma squared. Okay, so we have this distribution. Okay, so here n bar, so determine the position of the maximum, and standard deviation define the width of the distribution. Okay, so for example, for this one we can see that here, or in this case or this radiation, we can say that most of the mean value of the energy coming from the radiation is here. Okay, so you can see that if one, so a lot of radiation or radiation coming, and these are the energy, so there is a lot of energy here. So there is, if number 3, so we have a radiation, and each radiation has different energy. Okay, so lower energy. Okay, so for a given number of measurement, and standard deviation is defined as sigma prime equal to sigma over square root of n. So n, the n bar, the number of the mean of counting, okay, the number of radiation with this certain energy divided by the number of experiment that, or the number of detection that we did. Okay, so and the corresponding standard deviation is S prime equal to 100 over square root of n and bar. Okay, so here is again like in our PDA. So the probability of here the radiation with this energy is 68.3%. So let's say we want to kill the cancer with let's say 25 mega electron volt radiation. Okay, so these are 25 mega electron volt radiation, and most of the radiation that we alpha ray or radiation that we pass through the molecule is between this let's say 24.5 25.6. Okay, and here if we have Ne 95.5% within 2 sigma 5 and 99.7% to within interval plus minus 3 sigma. Okay, so here we can see that these are the energy of the radiation. Okay, so we can choose or we can fine tuning the meaning that we can fine tuning the radiation energy so that it will meet, it can penetrate our body, and it can interact with the cell of interest, and if that cell of interest is a cancer cell, so it can uh, distribute the energy from this radiation to this cancer cell so that the cancer cell can will we can kill the cancer cell. Okay, okay, and but in practice we always use the detector again, like I said, detector. So at an estimate precision of any single random measurement and I, so number of radiation with energy, certain energy, is given by this equation, sigma square root of 1 over n minus 1 n I minus n bar squared. So n bar equal to n I over n. Okay, so these are the number of experiment, and these are the number of photon for each measurement or experiment. Okay, so here the estimated precision. Okay, so how precise. Okay, so this one is to test the precision of our detector. Okay, so kalau kita macam kita punya COVID-19 the temperature, kita ambil temperature dekat kedai-kedai tu. Okay, so sekali kita ambil 36.3, the next one we get 35.9, the next one we get 37.3. Okay, so we random. Okay, so if we want the detector to get the same the same value 36.3, so we must be precise. Okay, so sigma equal to sigma over square root of n. Okay, and these are the equation. Okay, so here the expression value Ne of the measurement is not clearly the physically correct value, and in fact will not be if the measuring instrument is improperly calibrated or it otherwise biased. Okay, so macam saya kata temperature detector yang dekat kedai-kedai tu tak semestinya suhu kita yang ditunjuk dekat skrin tu mungkin it depends on the sensitivity or the precision of that uh, thermometer. Okay, so this one. So contohnya kadang-kadang kita dapat 37.5 ke atas. Okay. So N is correct as our experimental setup. So these are the example from our textbook, the textbook. So the standard deviation is due entirely to the stochastic nature of the field, since the detector count every incident rate. Okay, so here we can see that the detector is good, but the radiation is a for example, the spontaneous emission. Okay, so it can count only when the incident happen. Okay, so here the standard deviation is due entirely to the stochastic nature of the field, since the detector is 100% efficient. Okay, so